Welcome back to Derivability. Today we're going to take a look at 3D rigid body motion by taking a look at the angular momentum of a rigid body in 3 dimensions. Okay, the diagram style you may recognize from if you've seen some of my other videos. Okay, this is the first one I think as I've done for 3-dimensional rigid body motion. So you'll see the X, Y, and Z axes, and I'm trying to make things look kind of 3-dimensional. Also notice that the angular velocity vector is not merely a curly arrow in the plane. It's about a point. It is something 3-dimensional here in space. Okay, so we're going to need to know the kinematics. Like we always do when we do these sorts of analyses. Okay, the velocity of point I relative to O. Let's just say O is some convenient point. Okay, it's going to be omega cross R sub ig. Okay, that's the relative motion of I with respect to G in the rigid body, plus the velocity of G, the center of mass in this case, with respect to O. Okay. The angular momentum of this point, mass element dm, at point I, okay, that's r sub io cross mv here. You'll notice this mv as the linear momentum of the mass element m sub I at that point. Okay, so angular momentum is the moment of linear momentum, that is r, the appropriate r vector cross the linear momentum. Now, to get the angular momentum of the entire body, we'll sum over all the mass elements, okay, and really we're integrating. Okay, so h sub o, okay, for the entire body is going to be the integral of r sub io cross v sub io, and then the m sub I kind of shows up here again as the dm, the mass element. Okay, now we can write this as 2 separate integrations here. R sub io cross, okay, and then just let's imagine distributing this crossed into v sub io, distributed into each of those 2 terms. Okay, so r cross parentheses omega cross r sub ig dm plus integral r sub io cross v sub go dm. Okay, all right, now let's take care of that last term first, because that's the easiest, and that's really not where the meat and potatoes of this discussion is. Okay, now the v sub go is a constant, and that can be brought outside of the integration. So we're integrating r sub io dm, and then that integral, its result will be a vector, and that is going to be crossed into this vector v sub go. That's just the velocity of the center of mass, okay, which is a constant with respect to that integration. Okay, now this integral r sub io dm, okay, basically that's just the total mass times the position of the center of mass, and then that's being crossed into v sub go. Okay, another way of writing this is r sub go cross m v sub go. Okay, so once again here, you'll notice a term, something like we had here. Okay, so this m times v sub go, once again, is the linear momentum. Okay, and this cross product represents the moment of that linear momentum about, essentially the centroid, about some point O. Okay, all right, so let's save that. And then otherwise, we'll bring it back at the end. Otherwise, we're going to work on this integration. Okay, all right, so let's bring that right here for now. Okay, now r sub io, if you take a look at the blue vectors here, in terms of the vector addition. Okay, r sub io itself can be written as r sub ig plus r sub go. Okay, that replaces the r sub io, and then cross omega cross r sub ig dm. Okay. All right, so once again, we can kind of distribute the product through the sum that I have on the left. Okay, so integral r sub ig cross parentheses omega cross r sub ig dm. Okay, plus integral r sub go cross parentheses omega cross r sub ig dm. Okay, now again, the second of these is actually going to be the easier one to work with, and we'll take care of that one first, and then we'll come back to the first one probably on the next screen. Okay. All right, now notice here in this second integral that we have in red, the only thing that is a variable with respect to the integration is r sub ig. R sub go is simply this position of the center of mass relative to O. Omega just is what it is for this whole rigid body. Okay, it's not a function of from point to point. Okay, so this last integral here, okay, we can bring the r sub go out because it's a constant with respect to the integration. Parentheses, we can bring the omega out for the same reason, and then we have cross r sub ig dm. All right. Well, we saw an integral like this before, right up here. And what this is it's always going to be the mass of the body times the position of the centroid relative to some other point. Well, in this case, it's the position of the centroid relative to itself. Well, the centroid measured relative to itself is always the zero vector. So what that gives us, okay, we just get this integral to go away, meaning we just get this whole integral to equal 0. All right. Okay, so in a minute we'll come back and finish that first integral in the red writing. Okay, I need to create some clean space here. So hold on, and I'll be back with you in a minute. All right, got some clean space created. All right, now in blue, this is where we are, basically where we left off. Okay, the term we were working on, I've underlined in red, and then the term we had previously resolved following that in blue. Okay, but underlined in red, this is the angular momentum about the center of mass. Okay, in other words, if you take a look back on our previous screen, rewind, okay, the formula for H sub O, before we separated off this last term, basically had R sub IO in these two positions instead of R sub IG. Okay, well, that was H sub O. Okay, now that I've got R sub IG in both of those positions, well, it's H sub G. Now, we still have to do some work here, but that's just a intermediate step. Okay, so H sub G equals this integration. Okay, now what we can do is we can use the back cab rule that you may be familiar with to simplify this triple cross product. Okay, now that says A cross B cross C, okay, this is a vector identity. Okay, that is B times the dot product A and C minus C dot product A and B. Okay, all right, so of course, we've got our A, B, and C here. So H sub G, this becomes the integral of omega R dot R minus R, and then the scalar R dot omega dm. Okay, now at this point I am going to drop the subscripting here, r sub ig. Okay, let's just keep in mind that that's what they all are. All right. Okay, and let me now kind of simplify. I can simplify this a little bit. The r dot r is really r squared. Okay, and then the other term, that is the scalar magnitude r squared. The other term we can't really. All right. Now, this is a vector. The left-hand side is the vector h. Okay, the right-hand side, there are two things that have vector properties on the right-hand side, omega and r. All right, so probably the best way to continue here is just to focus on one component. So let's consider the x component. Okay, so I'll write that as h sub x, okay, kind of implied about g. Okay, so integral. All right, now omega, its x component, we could call omega sub x. But otherwise, r squared is a scalar, and let's just expand that out. Well, that's x squared plus y squared plus z squared in some coordinate. Basically, it's the x, y, and z coordinates of this mass element I with respect to g. Okay, but we don't need to worry about the subscripting details here. Okay, now the x component of the vector r is x, position vector, and then r dot omega, okay, well, that's the x component of r times the x component of omega plus the y component of r times the y component of omega, and so on, z. Okay, like this. Okay, now let me take an intermediate step kind of in between the actual steps here. And let me expand through all my parentheses, or most of my parentheses. Okay, so omega x times x squared, and then I'll just leave omega x times the sum, y squared plus z squared. And then over here, I'm going to have minus x squared, omega x, minus xy, omega y, minus xz, omega z. All right, and interesting thing here to see is that we get some of this to cancel. The x squared times omega x. So what this leaves is h sub x equals the integral. Okay, in fact, let me, if we start here, omega sub x, again, that's not a function of anything. It's just a property of the rigid body. So we have the integral y squared plus z squared dm. Okay, and then we have two other things. The omegas on these are constants with respect to any sort of integration. Then we have an integral xy dm minus omega z integral of xz dm. Okay. Now on the previous screen, we ran into a couple of integrations where we had like an r dm. Okay, and we found out that was related to the centroid. Okay, center of mass coordinate. Here we have integrations of the square or the product of two coordinates dm. Okay, well, those are related to the moments or products of inertia. All right, so I need to create some space here, and we'll pick that up again on the next screen. All right, we're back here. Okay, so h sub x I've rewritten up at the top. Now each of these integrals represents some sort of moment or product of inertia. So the first integral, integration of y squared plus z squared dm, this is the moment of inertia of the body parallel to the x-axis, and since we're talking about the centroid, through an x-axis that actually passes through the centroid. Okay, the y squared plus z squared is the distance squared from the x-axis to our mass element. Sometimes this is written as I sub x, other times I sub xx, for reasons you might observe here in a moment. Okay, the integral of xy dm, this is called the product of inertia, xy, And then likewise down here, integral of xz dm, that's the product of inertia x sub z. Okay, so these two guys are called products of inertia. Okay, and this first one, a moment of inertia. Okay, well, in any event, we now have a formula for h sub x. Okay, this h sub x is I sub xx omega x minus I sub xy omega y minus I sub xz omega z. Okay, now for very straightforward rotations about a fixed axis, essentially it's a two-dimensional rotation. Okay, you know, think about your introductory physics. It's basically what you're probably thinking of is something like this: angular momentum equals I omega. Okay, and that's true under certain circumstances. Okay, so for instance, if these products of inertia are equal to 0 for some reason, well, then you really do get back to this this good old intro physics formula. Okay, now just to complete the discussion, by symmetry we can write down formulas for components of the angular momentum in the y and z directions as well. Okay, now what I'm going to do is it's going to be convenient to write these angular velocity components in the same order, x, y, z, each time. Okay, so we're finding out here that for a particular direction, if we match the angular velocity component to that angular momentum component, well, what we're doing is we are including the moment of inertia about the corresponding direction. Okay, then otherwise the rest of the terms are negative, and we are getting a product of inertia whose double subscript, well, one of the subscripts corresponds to the direction of the angular momentum vector, and the other subscript corresponds to the component of the angular velocity. Okay, so I would challenge you perhaps to ponder that in terms of symmetry, what I've written down is correct. You know, maybe you would have a different way of writing that down, maybe in a different order to start with. Okay. Now what we could do, and I'm not going to, is we could write h a little sloppy here, excuse me. We could write h as a vector as h sub xi plus h sub yj plus h sub zk. All right, and then of course each of these three-term items will feed in here. You know, we'd have kind of like a 9-term sum. I'm not going to write that for h. I will talk about a special case here, though. Okay, and that special case is if the products of inertia just happen to be 0. Okay, so I'll underline all of the products of inertia in blue. Okay, now in that case, we really do get just a single term with, you know, an I times an omega for our angular momentum. Okay, so in other words, it's going to be I sub xx omega x, and that's the x component, so we multiply by I, plus I sub yy omega y j plus I sub zz omega z k. So even in this case, it's still not as simple as it would be for a fixed axis, essentially a two-dimensional or planar rotation. Okay. All right, one last thing here that you might ponder. If you're familiar with matrix arithmetic, matrix multiplication, then what we can do is we can think of obtaining h by taking a certain matrix times the vector omega with its three components. Okay, this matrix technically is called a tensor. It's called the inertia tensor. Okay, I won't write it down here because it really is not super necessary. It's a little bit more than a trivia question for most students in physics and engineering at this level, but it's also something that's accessible to most of you guys out there. Okay, so I am going to leave it here and just once again remind you that our result in general are these three components for this h vector, and then if you happen to have the special case where the products of inertia are equal to 0, it looks a little simpler. Okay, all right. Well, I hope this has been a helpful video for your studies in physics or mechanical engineering. Okay, I'd love to hear some of your comments. I'd love to have you as a subscriber. Okay, share this video with your friends and classmates, teachers even. Okay, and I'll see you around for the next one.